All right. Um, Quite a few more people today, and probably more joining us. Couple of things. Since there's more people, make sure you mute your audio unless you want to ask a question specifically. Um, I'm going to leave chat open. Please use it responsibly to ask questions or respond to me. Or just feel free if you do have a question during the lecture just to interrupt me. If you hold spacebar, it'll unmute you temporarily and then let go of it. It'll remute you. So it's like a push to talk. Yeah. Anyway, let's get going. So this is less of a lab like the one last week or any of the ones we did to the semester. It was designed by Joe and Eric, actually, and I think they did a really, really good job on it. As I read through it, it kind of really, the procedures in the worksheet really cover all the basics of what you need to know. But since I'd already kind of agreed to this, plus I figured it would be more like a traditional lab, I decided to do the lecture for it anyway. So this is something I did for specifically for my class last week for lecture or for lab 8, the fluorescence and spectroscopy one. And it seemed to help some people. So yeah, I'm glad to share it to the whole class here. So basically what you're doing this week is NMR spectroscopy. And this is a very, very powerful technique. It's very different than a lot of the techniques you've learned already in the semester in that it actually is more of a qualitative technique than a quantitative one. So if we start from the very beginning, what we're doing with this technique, the first thing to ask is, well, what's spin, right? So nuclear magnetic resonance. So we're talking about spin flipping nuclei of different molecules, right? And spin is something that is extremely confusing, right? We talk about it a lot. In chemistry, it's super important. It's important to physics as well. But what it actually is very complicated. So it happens to be an inherent property of particles, just like charge and mass are inherent properties of the base particle that you have. If we go back to the standard model that we talked about, like during nuclear chem, right? Every one of these fundamental particles has its own spin associated with it, right? Quarks have spin 1/2, fermions have spin 1/2, and then the boson particles and the force carriers have spin 1, integer spins, right? Nuclei themselves, though, are composite particles, right? They're made up, every proton and neutron is made up of several quarks and several up or down quarks, right? And they each have half integer spin, right? However, you can have multiple protons and multiple neutrons in a single nucleus, right? So what we're really going to be talking about here in this presentation are only nuclei that have half integer spins. Okay. Spin behaves like angular momentum. So the particle itself is not actually spinning. It just has extra angular momentum than you would predict based on classical physics, right? And to make things really, really complicated, the quantum mechanics that you learned about, right? You solve the Schrodinger equation, you get information about what's going on with these things, but actually it's not enough. The Schrodinger equation will not give you spin, right? If you were to solve the Schrodinger equation for the hydrogen atom, you get 3 quantum numbers. You get N, L, and M sub L, which tell you basically about the radius away from the nucleus, the angular momentum, and the specific positional angular momentum of the Z component. So that's really not, that doesn't lead anything to spin. What we do later is we tack on a spinner. The reason that we do that is because quantum mechanics is complicated enough on its own. And if we were gonna do things completely right and we wanted to get spin just from the basics, from the ground up, we have to consider special relativity. So spin is actually a consequence of special relativity applied to quantum mechanics. And if you ever go into higher level quantum mechanics courses, so this is like, I'm talking probably not even a year of graduate chemistry quantum, you would need a year of graduate physics quantum before you start to talk about relativity applied to these sorts of things. You'll also talk a little bit about it if you happen to be like a physics double major and you take upper division electricity and magnetism. But you will eventually get to this equation called the Dirac equation, which incorporates special relativity in these things. And that's where spin comes from. It comes out of the math of doing this equation. You get that extra parameter, which is your m sub s, and your, well, two extra quantum numbers, s, which is your total spin, and then m sub s, which is the z component of your spin, similar to L and m sub L, right? So what's interesting about spin? Well, if we go back to what we looked at last week, or at least the people in my class looked at last week, I made this slide for you, and I showed you how quantum mechanics tells us that energy in bound states in molecules, right, has to be quantized. It has to go to only specific energies and cannot go anywhere in between, right? And when you solve the different model systems of the Schrodinger equation for all of these different ways of storing energy, these three are the classical versions of storing energy kinetically, the three different ways you can move basically as a molecule. And this is your potential energy storage through Coulomb interactions, through electrostatics. The hydrogen atom is your model system. You get the energy level gaps and separations between all of these energy levels, right? And we learned that different kinds of light from the electromagnetic spectrum can be used to probe these different states of molecules, right? So when we use UV visible, we're usually talking about gaps in a molecule's electronic states, right? So we're actually exciting the electrons to a higher molecular orbital. We talk about infrared, we're talking about vibrations along a bond, right? That's what we're exciting, like rocking or wagging or stretching or bending motion along a bonding axis. So that's one way they can store energy. And those have smaller gaps, right? Similarly, microwaves are even smaller than that, and those are rotations. The reason a microwave works to heat up your food is because it's actually exciting one of the rotational modes of water over and over and over again, and that gets decayed as heat into the rest of whatever your sandwich, whatever you're heating up in the microwave, right? And I also mentioned that in order to do translational energy, because these gaps are so small, it's not very practical. You would need extremely long waves, something on the order of like what the LIGO detector can detect. Like it's really not practical. And as far as I know, no one is trying to do energy level spectroscopy for translational energy levels. They're just too tightly spaced. But where do these spin flips that we were talking about earlier fall into these? Well, we're missing part of the electromagnetic spectrum as we go on here, and the big portion here is radio waves, right? So radio waves would go in the middle here, and those are the frequencies that we would need to actually excite spin flips in nuclei. So what do I mean by exciting a spin flip? Because if you think about it, right, a spin 1/2 system, this is sort of your picture. You could have an up spin or a down spin, right? And they have the same energy. There's no difference, no preference or anything like that, right? Well, that's because we don't actually have a magnetic field applied. So if we were to apply a magnetic field to the system, let's say it's B naught and it's pointing up, the positive Z direction is usually how we denote that. Then all of a sudden the energy in these two states actually splits, right? So it's kind of like the d orbital energy splitting that you've been talking about in class, where one of these states now has lower energy than the other, right? And that's because we're changing the magnetic field around, and the spin up wants to align with that magnetic field, right? So it goes down in energy. Similarly, this beta, the spin down system, if it's pointing up, is where we actually have higher energy than we would have had before, right? So this is called the Zeeman effect, the splitting process. But what it allows us to do is now we have a gap in this energy, right? So like before, where we were doing spectroscopy by putting in energy into one of these gaps, now we can do that using our radio waves once we've applied a magnetic field, right? So that's why these NMRs have very strong magnetic fields. It's to create this splitting so that we can actually do these measurements. Okay, so I mentioned before it's radio waves, frequencies typically 50 to 500 megahertz that we would use for these kinds of transitions to happen. This energy gap is given by this equation, H bar gamma beta naught. Beta naught is the strength of the magnetic field that we applied. Gamma is the gyromagnetic ratio, which is the ratio of magnetic moment to angular momentum of this particular spin. So it depends on the particle itself and the surrounding magnetic field environment around it. So this is sort of an intrinsic thing to whatever molecule you're looking at. It's relatively constant over a large range of organic molecules, though. That's all the energy really depends on, right? So this gap is going to depend on the field strength and this gyromagnetic ratio, right? Okay, so then how does this actually work in an experiment? Well, the NMR, it's going to look something like this. If you go down to the basement in Latimer at some point, that we have a very large NMR facility here at Berkeley with tons and tons of instruments. But it is kind of a complex instrument. The first thing you notice is it's got this inner tube piece, right? This is where the sample actually goes down. You actually, there's actually hydraulic air that's pumped into this. I'm sorry, hydraulically driven air, I should say, compressed air that's pumped into this that allows the sample to move up and down as you want to take it out and put it back, put a new sample in. It goes into the center area where you have a magnet. And the magnet that you have, this is probably a little better picture of the actual magnet, is made of some sort of semiconductor material. Or I'm sorry, not semiconductor, superconductor material. And the reason for that is if you want to have an extremely powerful, strong, permanent magnet, the easiest way to do that is to actually have a semiconductor or superconductor material that has theoretically almost zero resistance, electrical resistance to it, and then apply a very strong current across that material, and that will charge your superconductor with a magnetic field, and it will actually hold that magnetic field. The problem with that is you have to keep it extremely cold. So you see liquid helium surrounding this superconductor material. Keeping it at roughly 4 Kelvin. That's the liquid helium temperature. That's where it boils. And then liquid helium is extremely expensive. So there's usually a jacket of liquid nitrogen around that to help further shield, and then vacuum around that to help even further shield your loss of helium that has to happen. So that's what makes these instruments so expensive is in order to maintain this magnetic field that was charged, which has a ton of energy stored in it, you have to keep it extremely cold. Otherwise, you run into a situation called a quench, where all of that energy that was stored in this material comes out at once, starts to evaporate all of that liquid helium, and then you have a really, really bad situation on your hand. Which is why these things have to be maintained quite well, and they're usually stored in basements to prevent any sort of problems with this. Also, that helium, as it boils, displaces the oxygen in the room, so people can suffocate and things like that. Anyway, this strong magnetic field, right, it aligns the spins around the sample tube. You have an RF transmitter that goes in. That's what actually sends your radio wave pulses to do that excitation. the way it works with this is you actually have a broadband radio wave pulse. So you're not hitting it with monochromatic radio waves. You're hitting it with all of the frequencies you're interested in measuring at once. And then what you detect coming out is, oh, by the way, this magnetic controller that you see, that don't be fooled. You do want a constant magnetic field. That's to what we call shim the field, or orient it in specific ways to make it constant around the entire sample. But anyway, yeah, so what you get out of it, though, is not what you expect from your normal type of spectroscopy. You get what's called a free induction decay, or FID, and it looks like this. Essentially, it's a whole bunch of different frequencies, all of the absorptions of this molecule added together, and you see it decaying over time, right? So the reason we get this is we have lots of equivalent protons on the molecule, which all absorb the same frequency, other ones that absorb different frequencies. So there's difference in intensity between peaks. Also, and this is sort of what causes splitting in peaks, there are those equivalent protons, hydrogens that are on the molecule, right? As this thing decays, it's excited, right? It wants to drop back down to the ground state, but that energy has to go somewhere. So it actually goes into, some of the photons go into like the solvent around it, go away as heat, but some of them end up getting reabsorbed into other hydrogens on the molecule. And it's sort of like an oscillatory decay back to the equilibrium ground state. So that's what you see in a free induction decay. But it's not super useful on its own. So what we usually do is we'll do a Fourier transform on it to break it down into its individual frequency components. So it's sort of like, let's just pretend this whole decay pattern was made up of all of these different cosine waves, right? Fourier transform, anytime you see transform in mathematics, basically it's saying we're changing the domain, the x-axis that we're looking at this in, right? And the way we do that is we're assuming that these little, any point on here is a little vector, right? On the time axis, it's showing the intensity versus time, right? We're going to project that vector onto a new axis, and in this case, that's frequency, and that's what the Fourier transform does. Is it tells us it's basically changing basis, right? So these are things that you have covered or will cover in some of your more advanced math classes. So like calculus 3, you probably did vector analysis. In linear algebra, you kind of took that vector analysis further and said, okay, well, we no longer just have 3 dimensions or however many. We can generalize these ideas like beyond that. And our axes no longer have to be just single variables. They can actually be functions as well. And that's what we're doing. We're saying, okay, this is one axis, this frequency of wave, this frequency of wave is another, this frequency of wave is another. How much overlap are there between it? So essentially we're doing infinite number of dot products is what this mathematical function is doing. It's checking the projection onto each frequency wave of this entire thing. And that's useful because frequency is directly proportional to energy, right? So we can compare the energies now, and we're able to do all of the wavelengths at once because of this Fourier transform. Right? Okay, so why does any of this matter at all? Well, I kind of alluded to it at the beginning, or maybe even straight up said it. It's great for telling us what the structure of organic compounds is, right? It's a great qualitative measurement for figuring out, okay, I have a molecule I made. What is it? What is its structure, right? That's what I want to know. So we typically will have a Fourier transform spectrum, right? And we'll also, at the same time in our sample, we'll put in something called TMS, tetramethylsilane, and we'll use that in order to find our reference point where what we call 0 ppm is. We'll divide our whole spectrum by that reference. And essentially we get a NMR that looks like this. And this is how it's typically shown. X-axis should be ppm. I don't know why it's not labeled here. Y-axis is intensity, which isn't very important to us, to be honest. We hardly ever use the intensity ideas of this, at least on a qualitative sense. In theory, just like any other spectroscopy, you could use this technique to quantify. However, it's a lot less sensitive. So it's generally not used as a quantification technique. Okay, so whenever we get a spectrum like this, and usually we won't know what we're looking at, but all of the worksheet problems have the structure already. We're trying to be a little bit nicer to you because this is your first introduction to this, plus you're going to get tons of experience with this in organic anyway. But essentially, this is sort of what you'll see. They'll give you some peaks, and they'll give you the molecule, right? And it's your job to assign what hydrogens in a proton NMR go to which peak, right? So what you want to do is, the first thing you want to do is label the equivalent hydrogens in these molecules. So for this, you can see all three of these dark blue hydrogens that are labeled here that are on this methyl are equivalent. They have the exact same electric field, magnetic field around them as each other, right? You can think they're coming off the methyl, like, I don't know if you can see my camera, but like that, right? So they're all equivalent hydrogens. And similarly, the two on this carbon are actually the same, and we have this hydrogen that's not like any of the others. So we have three different groups of hydrogens, right? So we would expect 3 peaks in our NMR, and that's actually what we see, right? The next thing that you want to do once you've identified the equivalent hydrogens is you want to see where these peaks are located on the ppm scale, right? So the deal with ppm is 0 is our tetramethylsilene reference that we start with, and we want to know how far away we are from that reference, right? If it's closer to that 0, we call it upfield. If it's further away, we call it downfield, right? And this is all, we call the reason it goes upfield or downfield is due to shielding, right? So what we mean by shielding in this case is how much influence from the magnetic field of different functional groups are there next to these hydrogens, right? And that's what determines how far upfield or downfield it is. So electronegativity is a big part of that. Obviously, lone pairs are a big part of that. The size of the atom itself is a big part of that. So there's a lot of things that go into this, right? But because organic molecules have basically the same functional groups, we can generally start to characterize where on this ppm scale these different functional groups fall, right? So let's see what we have here. Well, we have an alcohol that's shown right here. So it's anywhere from 1 to about 5 ppm. So that's a pretty big range that it could fall in. It depends on a lot of things. We have just a general alkene right here in the CH3, right? So that's what's going on here. And this is very upfield. This is actually anywhere from like 0.1 to roughly 2 ppm, right? So these hydrogens we would expect to be very upfield. And then we have this one in the center, which is like this, where X can be O, N, F, any of these, right? That is very similar to, or these hydrogens here are equivalent to this hydrogen here that it's stalling out, right? So this is actually a little more downfield than your traditional alkene hydrogens would be. And these fall roughly between, in this case, 2.5 and 4.5, right? So that's where we expect these kinds of things. So are there any that are easy to explain this way? Well, I think the first thing we can look at is, okay, we expect this to be much more upfield than the others. It could be that this OH isn't. But we usually expect this to be as much upfield as we can. And the one right here by 1 is this peak here. So I'm tempted to like assign this peak right away. But there's something else that can help us assign that, and that has to do with the splitting, right? So as I mentioned before, splitting occurs because of nearby hydrogens, right? So if we look at the splitting patterns, right, a basic singlet means that there's no other nearby hydrogens that nearby shielded hydrogens, I should say, that to create the splitting pattern. When we have 1, we get a doublet, so we get 2 peaks, the peaks split. When we have 2, we get a triplet, right? And when we have 3, we get a quartet, right? So the other evidence I have is that this peak right here is actually a triplet, which means these hydrogens have 2, or if this assignment of these hydrogens is for this peak, they should have 2 nearest neighbor hydrogens 1 carbon over, and it happens to do that, right? So this is our triplet assignment, right? That's assigned to this alkene, right? So it's in the right range. It also has the right splitting pattern. So that's what we can say about that, right? Okay, so the next question is, okay, well, this OH can also coincide with the other guy here, right? So which of these peaks is the OH, the alcohol hydrogen, and which is the CH2 hydrogens, right? And again, from before, we know that our CH2 has 3 nearest neighbor hydrogens, right? So we would expect it to have a quartet splitting pattern. And that's exactly what we see, right? And this is pretty common. If you have a triplet here, you should have a quartet matching it, right? There should be pairs of these splittings to show that these are nearby hydrogens, right? If this one gets split by this one, then the other one gets split by the other one. That's something that you should expect to see, right? So then we would assign this to be our CH2 hydrogens, right? And our last peak, which is a singlet, and it's a singlet because of this oxygen molecule. It's not on a nearby. You have to basically jump over this O molecule to get to the next nearest carbon. So we would say that it has no nearest proton neighbors, and we would assign that to be a singlet. So this is the basic gist of how this goes. I think the worksheet is a really good reference for this. Basically, this is how all of the last few problems in the worksheet are going to go, is going through these steps. And I think, like I said, it has a couple of examples, and then I think it helps you work through the problems fairly easy, similar to these with small molecules. So I don't think it's too terribly difficult. But yeah, that's what NMR is used for. That's really all I have for you. Like I said, I think the worksheet itself is a pretty good reference this week. I wanted to add some of the basics from the beginning, but I don't think that it's too terribly, what is it? Like the worksheet itself, the way it's written, I think isn't too terribly difficult to work through. But yeah, here's my office hours. Obviously, my class already knows what they are. They're normal Pacific Standard Times. I'm still here in Berkeley. Here's my email if you want to email me. Obviously, your own GSIs are good references on this, especially if you have GSIs that are synthetic chemists. They use this technique all the time, all day long. Probably much better than me. I can talk about the theory a bit, but I'm not great at actually. I don't have the experience using the instrument like that they have. I've done it, a dozen to 15 times in my life, but never every day like they do. Yeah, at this point I can take any questions if you guys have any. If not, then we'll call it.
Steve, for the energy equation, like what's H bar?
H bar is Planck's constant divided by 2 pi.
Okay.
So it's a condensed notation, but it's pretty common in quantum to, whenever you see H divided by 2 pi, because it's so common, we just write H bar.
Okay.
Hi. For the ratios of the splitting, like the alpha and beta states, on the lab I kept on getting values that were like 0.999 something, like basically 1. Does that seem accurate, or does that seem like not accurate?
I didn't work through the problems myself yet, but it depends on the exact situation. So if you're getting ratios of like everything's 1, that makes sense if there's a strong B field applied, right? Because everything wants to be in the ground state and everything's alpha. However, if, you know, there is free energy around, so some of it can absorb and flip a spin, but it's just less likely. So it really depends on how big this energy splitting is and how strong this, which depends on how strong the B field is, right? So I'd have to look at the numbers to tell you exactly.
Okay, thank you.
And also, can you send out the slides?
Yeah, I'll send out the slides. Also, I think Shane's going to post it on B courses, and I'll send the link and everything like that for that. So.
Hi, Steve. So, is a nucleus considered less receptive if the energy gap is smaller between like the alpha and beta?
Less
receptive?
By receptive, do you mean susceptible to transition, or what are you talking about?
I don't know. It's a question in the lab. They ask, is C, the 13 isotope, more or less receptive as a nucleus?
Oh, I think are they trying to compare it to other nuclei?
Yeah, they're comparing it to the hydrogen.
Okay, so I think then what you should be thinking about is there's like a paragraph before that question that talks about what makes a good candidate for an atom that we would look at in NMR, right? Like, what are the things that they go through, right? One of them I already gave away in this slide already is like spin 1/2 is better for this sort of thing, right?
Okay, so it's not
easier to
related.
understand. It's to the gap energy itself. I would say it's not really, right? I would go back to your table that you filled out, and I would look.
Because the question says compare the like delta E.
Does it really?
Yeah.
I should get that in front of me. Then I will look into that and get back to you.
Okay, thank you.
But I will say this, right? Like, the larger this gap, the more likely things are going to be in the ground state until you hit it with the energy required, right?
Okay, so in that case, would it be better if it's a smaller gap so then it would split easier?
Yes. Well, it doesn't split easier. It's just like it's going to split when you apply the B field, right?
Mm-hmm.
It's just, if it's a smaller gap, you have higher probability of being able to populate the higher state, right? That's all that means.
Okay, I will look at outside resources then as well.
Okay, yeah,
But
I'll email you too. So
okay.
once I look at it directly, have it in front of me.
Cheers.
Okay. Anything else? Okay. I think we'll call it here then. Thanks everybody for coming.
Bye, Steve.
Bye.
Thank you.
No problem.
Thanks, Steve.